Alright, today we're going to have a look at a strategy called splitting the numerator. So, there are two methods that we're going to use in terms of splitting our fractions into multiple fractions. Number one is splitting the numerator, which is a tad easier, and number two is called partial fractions decomposition, which is where we're splitting up the product of the denominator up into two separate things instead of one product. So case number one, when we split the numerator, is if the degree of the numerator is greater than or equal to that of the denominator. So if the highest power on the top is bigger or equal to the one on the bottom. If we do that, we need to somehow rewrite the numerator as multiples of the denominator, or just the denominator. We can do that a number of ways. Number one is by factorizing. Now notice in this one we can't factor. We could factorize to give x plus 2x, x plus 3x plus, or x minus 1. And actually no, we couldn't quite factorize the top. The discriminant of that is going to be too big. It's going to be less than 0, so we can't factorize this. But I could factorize this, and this is where it can get a bit tricky. I could factorize this. X squared plus 2x. I definitely could factorize that on x minus 1. You're thinking, how on earth would I know that? Well, I know that if I factorize this, I'm going to get x minus 1 somewhere, which means that will cancel. So if I do that, I need a plus 6. So this is the integral of x plus 3, x minus 1, plus 6 over x minus 1, which is the integral of x plus 3, x minus 1, over x minus 1, plus 6 on x minus 1. Now those two integrals are very easy. This is just the integral of x plus 3, which is x squared on 2 plus 3x. And the next bit is plus 6 ln of x minus 1 plus c. Nice and easy. Example number 2, the integral of x plus 2 on x plus 1. Here we've got the degree of the numerator is equal to the degree of the denominator, so this is much easier, and we're going to employ this strategy, which I've shown you in extension 1 many times. This is x plus 1 plus 1, because 1 plus 1 is 2, on x plus 1 dx, which we could say is 1 plus 1 over x plus 1, because x plus 1 and x plus 1 is 1. And that simply is x plus the natural logarithm of x plus 1 plus c. Example 3, we've got the same scenario. So this would be the integral of x squared plus 1 plus 4 over x squared plus 1, which is 1 plus 4 on x squared plus 1. And this is just 4 lots of 10, or the tan integral. So this is x plus 4 lots of tan inverse, or arctan, of x squared plus 1 plus c. Okay, the next example, we're looking at the integral of e to the 2x plus e to the x on e to the 2x minus e to the x. Again, we're going to try and write the numerator in terms of the denominator. So this is the integral of e to the 2x minus e to the x plus 2 lots of e to the x on e to the 2x minus e to the x. Of course, this is now going to be the integral of 1 minus 2 lots of e to the x on e to the 2x minus e to the x. Now the problem with this question is the e to the 2x. If you differentiate e to the x, we'll get e to the x on the top. So we want to think, how can I get rid of e to the 2x? The strategy we're going to use is by multiplying everything by 1 on e to the 2x. So we're kind of like rationalizing the denominator here. So this is the integral of 1 minus 2 lots of 1 on e to the 2x is e to the minus x over 1, because e to the 2x on each of the 2x is 1, e to the minus x dx. Now we move that up to here. If we differentiate that, we get minus e to the minus x, which is actually what we've got on the top. So if we differentiate that, so 1 minus e to the minus x, actually, sorry, that should be a plus there. That's why I'm getting confused. That's going to be a plus there. So if we differentiate that, we get minus e to the minus x. So we need a minus here, a minus up here, which means we need to make this a minus. So this is just simply x minus ln of 1 minus e to the minus x plus c, because the differentiation of the bottom is now on the top. Case number 2, if we've got the numerator, the degree of the numerator is 1 less than that of the denominator. Now, if the numerator has a degree that is 1 less than the denominator, then we just rewrite the numerator as multiples of the derivative of the denominator, and that will get us our ln form. So the derivative of the denominator is 2x plus 4. So ideally we want 2x plus 4 on the top, but we don't have that. On the top we've got 4x, which in terms of the x term is 2 more than we want. So let's write, okay, 2x plus 4 is what we want on the top. Let's write that there. But we've actually got 4x on the top, so we really have to times everything on the integral by 2. Now we don't need to put a half out here because 4x was already on the top. But since there's a 2 here now, that would be an 8, so we need to subtract 8 from that integral. So this is now, let's bring this 2 out to here. 2 lots of the integral of 2x plus 4 on x squared plus 4x plus 13 minus 8 lots of the integral of 1 over x squared plus 4x plus 13. Now that's 2 lots of the differentiation of the bottom is now on the top, so it's the natural logarithm of x squared plus 4x plus 13. Now if we just look at the bottom here, we're thinking completing the square. So if we complete the square on that, we're going to have x squared plus 4x plus 4 divided by 2 is 2, squared is 4, plus 4, and of course instead now it's going to be plus 9. So the bottom is going to be x plus 2 all squared. Oh, go away. Goodbye. X plus 2 all squared plus 3 squared, which is just tan inverse, in the form tan inverse. So we're going to have minus 8 on 3. So the 8 comes from here, and the 1/3 comes from there. Tan inverse of x plus 2 on 3 plus c. Loved that integral, that was nice. Okay, the last strategy that we're going to informally learn here is partial fractions. So partial fractions by inspection involves undoing cross multiplication. So we could easily integrate something over x plus something over x plus 1. We need to think to ourselves, what would I need on the top so I would get 3? If I cross multiplied this up here, I'm going to have, if I cross multiplied this up to here and that up to there, we're thinking what would we need on each one of them. So if, for example, if we had a 3 here, that would get us 3x plus 3, and then to undo that we would need to put a minus 3 there, because then we would have 3x plus 3 minus 3x. So that's just equal to 3 ln of x minus 3 ln of x plus 1. Easy. We're going to formally learn how to do that in the next video. Question 7. Again, we got the integral, and we're going to split it up into 2 fractions. We've got to think to ourselves, what would we need? We want a 1 on the top, which means we want an x squared to cancel if we put a minus here. So we might need an x here because x times x is x squared, and if we put a 1 here, we're going to have x squared plus 1 minus x squared will get us 1. So that's ln of x minus, the differentiation is almost on the top, we've got to put a 2 here and a half here, minus a half of the natural logarithm of x squared plus 1 plus c. Okay, thanks for listening.